All right, hello. Today we're going to talk about wave diffraction, particularly when we're talking about light. We're talking about the double slit experiment and the nature of light. Exactly what is light? Is it a particle or is it a wave? All right, so first things first, diffraction. Diffraction is a wave phenomenon like refraction, reflection, interference, any of those things. But it occurs when a wave bends around an obstruction. Something's in the way of a wave. If part of it can get through, then it spreads out and bends around an obstruction. So if you look at the picture here, the waves are coming in straight here, and then they reach these little walls, but there's a hole in the wall. And if you notice, the waves kind of spread out in all directions to fill in kind of that empty space. Right, in this picture over here, we kind of see a real life version. You see these straight, pretty much straight water waves coming in, and then you got these little bits of land, but there's some openings. And notice that when the water reaches that point, it spreads out and it curves, and you see it, these waterways kind of spread out to these empty spots. All right, so I've got two figures here. Diffraction, how much diffraction occurs depends partially on how big the opening is for the waves to get through. All right, so if we look at the first picture here, if we look at that distance and that distance, they're not exactly the same, but they're fairly close. They're close to being the same. And what happens is when the opening is around the same size as the wavelength of the wave, and of course this right here is the wavelength of the wave, the waves diffract quite a bit, a lot. And it just means that it spreads out more, filling in these empty spots a lot more. All right? If we have a larger gap, notice here that this distance is much larger than that distance, the wavelength. And notice that the waves still diffract, the waves still spread out, but they spread out just a little bit. All right, so when the opening of the obstruction is large compared to the wave, or compared to the wavelength, the waves diffract just a little bit. They spread out less than what they normally would. All right. Now, this is really important because when we talk about light, most of the time when we see light going through openings, going around obstructions, through a window, or when you see shadows being formed, those openings are really, really large compared to the wavelength of light. The wavelength of light is really, really small. It's like 10 to the negative 10, negative 15, depending on what type of light it is, if it's what type of electromagnetic wave. Okay. But in other words, the wavelengths are very, very small. All right, so if you look at this picture here, here's light coming in through a partially open door. Okay, or through, and this could be a window too, right, and into a dark room. You can see right here that there's very distinct boundaries between the light and the dark where the shadow is formed. Okay, there's not a whole lot of diffraction going on. The light is not spreading out around this obstruction. Right, you see it's a little bit of light because some of the light comes in, it bounces off the walls and such, and it lights up some of the other parts. But for the most part, you see this clear distinction between light and dark. So that means there's no diffraction, or not much diffraction going on. All right, and this is important. Why we don't normally see this with light, right? And that's also will explain why it took a long time for people to really understand that light is actually a wave. So which leads us to the next topic. All right, so nature of light. Is light a particle or is it a wave? It kind of depends on how you look at it. Okay, optics treats light as if it were a particle. Everything moves in a straight line, just like a ball has been shot out of a launcher. Okay, until something goes in a straight line, until something changes its motion. For light, it could be something like a lens or a mirror or something, and that's going to make it change direction. All right. Sir Isaac Newton was a big supporter of this idea. He called these light particles corpuscles. I don't need to know that word, but it's kind of fun. All right, so this debate about whether light was a wave or if light was a particle went back and forth for several centuries until a guy named Thomas Young proved that light was indeed a wave. right? And the experiment he did was known as the double slit experiment. We're going to talk about this very, very briefly, right? And so what happens here is that light was sent through two very narrow slits that were really, really close together. This is exaggerated. The two slits are really, really, really close together, less than a millimeter apart. And these slits are very, 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 very narrow. We're talking about a tiny little fraction of a millimeter, right? But enough for the light to go through. The light's going to go through both of these, right? Now, here's kind of what would tell us. If light was a particle, if light behaved like a bunch of rocks, then it will act like a bunch of rocks. If I were to throw a bunch of rocks through two windows, when the rocks that got through those windows, if we marked where they hit every single time, we'd have an area here and an area here where those rocks would hit it, because the rocks aren't going to spread out when they go through the window. They're just going to go in a straight line, right? So this is what you would expect to see if light was a particle. Okay. What Young discovered, though, is that it didn't work like that. What he, if light was a wave, this is what he actually did discover. It's going to display wave properties like diffraction and interference. Right. So what really happened was, as the light waves came in here, as they went through these thin slits, because these are like obstructions, the waves spread out, filled in those empty gaps on either side. And so they spread out. So we have light waves coming from this slit, light waves coming from this slit. And as they kind of fill in this middle section, they start to overlap one another. All right. So we see this diffraction. And then when they overlap one another, we begin to see interference. If you remember that from the last unit, that's where two waves occupy the same space at the same time. We have constructive interference or destructive interference. All right, so Young showed that when light was sent through two closely spaced narrow slits, the patterns of alternating bright spots and dark spots appeared on either side of the slit. And they looked really just like this picture here. This top one is using red light. We see the center part, a bright area with red, and then on either side of it, a very dark area that has no light, and then some not quite as bright spots, then dark, then bright, then dark, then bright, etc. Right? And so this showed two things. It showed that light diffracted, meaning it spread out from the slit, and that light interfered. Right? The bright spots, the light spots here. Let's change the color. This spot, this spot, this spot, this spot are all constructive interference. And then these areas in the middle, where there's no color at all, where there's no brightness at all, were destructive interference. And this was a huge discovery. It showed that light was a wave. Okay, so this experiment shows that light is definitely a wave because it both diffracts and interferes. But if we go back and looked at Snell's law, remember that when we had the light entering, do that there. We have some sort of substance here like water, and light comes in like that. We know that it changes direction, right? It moves in a straight line. So Snell's law tells us that light must also act as a particle. And so which one is correct? They both are. Right? We call this wave-particle duality, right? Which is one of the really, really interesting things. And if you study physics in the future, you might have a class that talks more about this, but we won't go into that in this class. But it is a fascinating subject, right? But what you need to get from this is that the experiment that Young did showed that light was a wave, that it behaved like a wave.